So welcome to the gate class. In last class we have studied. So welcome to signal and system gate class. So in last class we have started the discrete time system. So today we will start properties of discrete time LTI system. Properties of discrete time LTI system. So first property, the very first property of discrete time LTI system is system with or without memory. System with or without memory. So since the output yn of a memoryless system depends only on the present input xn then if the system is linear and time invariant, then if we consider linear and time invariant system, if we consider the linear and time invariant system, the relationship is presented as yn equals to k times xn. This is equation number 1. So what is k? So where k is a gain, and it is basically constant. Okay, thus the corresponding impulse response is simply Hn is equals to k times del n. So therefore if Hn naught is not equals to 0 for n not equals to 0, then we can say that discrete time LTI system has memory. Okay, so what is the condition? If the condition is if Hn naught is not equals to 0 for n not equals to 0, then we can say that the discrete time LTI system has memory. Okay, So this is the property of system with or without memory. So this is equation number 2. Okay, this is equation number 2. Okay, next property is causality property. Next property is causality property. Next property is causality property. So similar to the continuous time, similar to the continuous time case, the causality condition for a discrete time LTI system, is given as Hn equals to the impulse response equals to 0 for n less than 0. So what is the condition? The condition is the impulse response is equals to 0 for n less than 0. So this is equation number 3. So now we are going to apply this causality condition. Now we can apply this causality condition given in 3 to the convolution sum operation, to the convolution sum operation. So what is that equation? Convolution sum. It is yn equals to hn convolution with xn. So we have this discrete time system, we have discrete time LTI system. Here you are applying an input xn, the output you are getting is yn, and the impulse response is hn. So this yn is nothing but the convolution of hn with xn. And also it can be represented in this summation form, that is k equals to minus infinity to plus infinity hk x n minus k. Okay, so if we apply this property, that impulse response, we are considering that the system is causal, so the impulse response is 0 for n less than 0. If we apply 3 into 4, now substituting 3 into 4, we get, so what we will get? So we will get yn is equals to summation k equals to 0 to infinity hk x n minus k, and also yn is, and also we can write it in this form, yn equals to k equals to infinity to n xk h n minus k. So we can write in both form, we can write both forms are equal. So what is that? That equation 5 shows that, so the expression 5 shows that the only values of the input, the only values of the input, the only values of the input xn used to evaluate the output yn, used to evaluate the output yn are those for k less than or equal to small n. Okay, so this is our causality condition. So as in case of continuous time case, we say that any sequence xn is called causal if xn equals to 0 for n less than 0. So let us write it. So in next page, so as in continuous time case, we say that any sequence xn is called causal if what is causal signal if xn is equals to 0 for n less than 0. So let us take an example of causal signal. If you have xn is equals to un minus 1. So if we plot this graph of xn, if we plot xn with respect to n, then what we will get? We will get this type of graph, 1 2 3 4 up to infinity. So if we see that graph, here xn is equals to 0 for n less than 0. So this type of signal is called causal signal. So this type of signal, so this is causal, and it is called anti-causal, and it is called better to write in this form, and xn is called anti-causal, and xn is called anti-causal if xn is equals to 0 for n greater than or equal to 0. So the signal which is 0 for all the positive values of n, then this type of signal is called anti-causal signal. So an example, if you have xn equals to del n plus 1. So if you have a unit sample signal located at n equals to minus 1, so if you have this type of signal, then you can say that for for n greater than or equal to 0, xn is equals to 0. So this is called anti-causal signal. So this type of signal, this is anti-causal signal. So the signal will lie only on the negative side from minus infinity to minus 1. It can take values, and from n greater than or equal to 0, that is, it is 0 from n equals to 0 to n equals to infinity. So from n equals to 0 to n equals to infinity, that xn is 0. So this type of signal is called anti-causal signal. This type of signal is called anti-causal signal. So thus when the input xn is causal, thus when the input xn is causal, the output yn of a causal discrete time LTI system is given by yn is equals to summation k is equals to 0 to n hk x n minus k is equals to k equals to 0 to n xk h n minus k. Okay, so if this is xn is a causal signal, then instead so basically if in general condition what we are writing yn is equals to summation k equals to so what is generally yn? Yn is equals to summation k equals to minus infinity to plus infinity xk hn minus k. But since this is a causal signal, so we are represented yn in this form, that is yn is equals to summation k equals to 0 to n hk xn minus k, or from also we can write it in this form k equals to 0 to n xk hn minus k. Both are same. Next property is very important property. That property is called stability property. So what is the stability property? So it can be shown that a discrete time LTI system is bounded input, bounded output, stable if its impulse response is absolutely summable, that is summation k is equals to minus infinity to k is equals to plus infinity, modulus of hk is less than infinity. So if our impulse response, if we integrate from k equals to minus infinity to plus infinity, the impulse response, the value we are getting, the summation we are that summation value we are getting, it should be bounded. It should be bounded. So this is called BIBO stability. So what is BIBO? Basically that if we are giving bounded input, then obviously we are getting the bounded output, then the system is stable. So BIBO means bounded input. B stands for bounded, then I for input, then again it is bounded. O stands for output. So next is our eigenfunctions of discrete time LTI system. So in case of continuous time LTI system, we have discussed that eigenfunction and eigenvalues. Likewise here in discrete time LTI system also, we are going to discuss the eigenfunctions of discrete time, means eigenfunctions and eigenvalues. So eigenfunctions of discrete time LTI systems. Eigenfunctions of discrete time LTI systems. The eigenfunction of discrete time LTI system, the eigenfunction of discrete time LTI system is represented as if we put system operator inside the system operator, if we apply the input as Zn, then we are represented as lambda z raised to the power n. If we are getting this type of representation, then this is representation to find out the eigenfunction of discrete time LTI system. So what is lambda? Likewise in continuous time case, here also that lambda is basically the eigenvalue of the system associated with z raised to the power n. So where lambda is the eigenvalue of system as discrete time LTI system associated with z raised to the power n. So let us recap the LTI system. So that LTI system is just like we have this xn, then this is our LTI system, and we are getting yn, the impulse response is hn. So yn is nothing but transformation, the system operator inside we have xn, that input we are applying. Now what we are taking, we are setting xn is equals to z raised to the power n. So what we are getting if we apply this xn is equal to z raised to the power n in this LTI system, so what we will get? We will get yn yn is equals to, what we will get, yn is equals to system, inside the system operator we have input z raised to the power n. So finally we have yn is equals to, that is system, under that system operator z raised to the power n. So basically we are applying the input as z raised to the power n. So xn is equals to z raised to the power n. This is your LTI system. Then we are getting the output yn. So what we can write? We can write it in the form of convolution sum. So we have summation k equals to minus infinity to plus infinity hk z raised to the power minus k. Then we have yn is equals to summation k equals to minus infinity to plus infinity hk z raised to the power minus k z raised to the power n. So basically we have this, we have used that instead of this xn, we have applied that z raised to the power n. So finally what we can what we will get, we will get yn is nothing but it is hz multiplied by z raised to the power n. So it is nothing but lambda z raised to the power n. So hence we have proved that relation that we have given in previous page. So in previous page I have given the relation that if we apply the input z raised to the power n, then we are getting this output, that is lambda z raised to the power n. So, and what is lambda? Lambda is basically the eigen value. So lambda is basically the eigen value. Now a very important concept arises from this is that okay, so where I will tell you what is that important point. So before that, what is that lambda? So basically lambda is hz, and it is nothing but just like in our continuous time LTI system, we have lambda equals to hs. So in our continuous time system, if you remember, we have lambda equals to hs. So that is just Laplace transform of the ht. So what is hs? Hs is nothing but the Laplace transform of ht. Likewise here, this is our z transform. So simply it is summation k equals to minus infinity to plus infinity. We have hk z raised to the power minus k. So thus the eigenvalue of a discrete time LTI system of a discrete time LTI system, thus the eigenvalue of discrete time LTI system associated with the LTI system associated with the eigenfunction, z raised to the power n is given by hz. Okay, so the eigenvalue is nothing but it is equals to hz. It is equals to hz. So So what is hz? So hz is a complex constant, is a complex constant whose value is determined by the value of z, whose value is determined by the value of z. Also that important point that I told you is that if we put n equals to 0, then what we will get? We will get y0 is equals to hz. If we put n equals to 0, we will get y0 is equals to h of hz. So because if we see the expression, if we put n equals to 0 here, if we put n equals to 0, what we will get? We will get y0 is equals to lambda z raised to the power 0. And what is lambda? Lambda is equals to hz. So if n equals to 0, we have y0 equals to lambda, and that is equals to hz. So the so y0, so at n equals to 0, it is equals to the eigenvalue. So now we can solve some problems. related to LTI system, discrete and continuous time LTI system. So let us solve some problem related to continuous time LTI system, and after that we will solve problems related to discrete time LTI system. So the problem is, let us write down the problem. The input xt and impulse response ht of a continuous time LTI system is given by xt is equals to ut and ht is equals to e raised to the power minus at into ut. And what is a? A is greater than 0. Now what is the first question? First part of the question: compute output yt by the relation yt is equals to the relation yt equals to xt convolution with ht. Again, for the same given values, compute yt that is equals to ht convolution with xt. So we have to compute the output for two given relation. That first relation is yt is equals to xt convolution with st. Second is that if we apply the commutative property, then xt convolution with ht is equals to ht convolution with xt. So we have to we can compute yt by both formulas. Okay, so let us solve this problem. So let us solve this problem. So let us solve first part. So first we are going to draw the diagram. We are going to draw the diagram of xt and ht. So x tau, let us take x tau. Why I am taking tau? Because yt is nothing but it is a minus infinity to plus infinity. Since we are considering the first part, so we have yt is equals to x tau ht minus tau d tau. So what is xt? So xt is ut, and what is ht? ht is equals to e raised to the power minus at into ut. Okay, and a is greater than 0. So what is x tau? So x tau is like this. And what is h tau? So h tau is a decaying exponential. The maximum value is 1 at t equals to 0, tau equals to 0, the maximum value is 1. Here tau equals to 0, the value is 1 throughout that tau in positive side. And this is our decaying exponential. This is h tau. So okay, so this is our ht, this is our x tau, and this is our h tau. Now please note that I have taken that tau axis. Please note that independent variable I have taken tau, because in that integral we have x tau. What is yt? Yt is basically minus infinity to plus infinity. X tau ht minus tau d tau. So this is part A. Basically in part A we have yt is equals to xt convolution with ht in part A. So this is our x tau, this is our h tau. Now we need ht minus tau. So how we can write ht minus tau? So we consider both the cases. So what is ht? How to write? How to draw ht minus tau? So ht minus tau, if we consider that tau, if we consider t less than 0, if we consider that t less than 0, then it is like this. And if we consider that t greater than 0, then it is like this. So this is our t point, this is also our t point. So this is ht minus tau. This is ht minus tau when t greater than 0, and this is ht minus tau when t less than 0. So this is figure 1. Now maybe you have confusions how to draw this ht minus tau. So let us explain this ht minus tau. So how this ht minus tau will come? So you just plot the h tau, then time reverse. Then time reverse this h tau, we will get h minus tau. After that, if we shift it with t, then we will get ht minus tau. So what is h tau? So h tau is this is our decaying exponential h tau. It is 1 only, 1 point. Okay, now what is h minus tau? H minus tau is just the mirror image. It is reflected and from the origin. This is h minus tau. Now we have two cases. First case is if we consider that t greater than 0. So write in next page. So this is our h minus tau graph. This is our h minus tau graph. Now if we consider for t less than 0, if we consider t less than 0, then the shift is obviously in we should go away from the origin in towards the left hand side. So this is our ht minus tau when we have tau, that is when we have t that is less than 0, that is t is negative. The amplitude will not change, it will remain 1 only. Now for second case, when we have t greater than 0, then what is happening that this graph will shift in positive side. Graph will shift in positive side. So we have this the shift is in positive side because we have t greater than 0. So this is ht minus tau, and it is shifted with t point. It is shifted with t point. Now this is graph of ht minus tau. So let us solve the problem. So as x tau and ht minus tau is given in figure 1, considering both the cases when t greater than 0 and t less than 0, is given in figure 1, considering both cases when we have t greater than 0 and t less than 0. Now from figure 1, so in figure 1, if we see the figure 1, this is our figure 1. So if we see the figure 1, if we have x tau, if we consider t less than 0, if we multiply x tau with ht minus tau, what should be the result? Is there any overlapping region? So x tau and ht minus tau do not overlap for t less than 0. It is clear from the graph. We can see that for t less than 0, let us again draw the graph. So for t less than 0, this is our x tau, this is our x tau, okay. So from figure 1, this is our x tau, and this is our ht minus tau. For t less than 0, so from figure 1, for t less than 0, x tau and ht minus tau do not overlap. So from figure 1, we can see that x tau and ht minus tau do not overlap. Okay, so we have yt is equals to minus infinity to plus infinity x tau ht minus tau d tau is equals to 0 for t less than 0. Now consider the case. So for t greater than 0, what is the graph? From figure 1, the graph is, this is our x tau and this is our ht minus tau. So this is our graph for t greater than 0. Now for t greater than 0, now for t greater than 0, they overlap. So x tau and ht minus tau are overlapping when we have t greater than 0. And what is the reason of overlap? So this is our x tau and this is our ht minus tau. Now if we find out that overlap region, so this is our t, here we have t. So what is that region of overlap? So basically if we multiply these two graphs, then we will get this area. So what is the region of overlap? It is overlapping between 0 and t. So while for t greater than 0, so while for t greater than 0, they overlap from tau equals to 0 to tau equals to t. Hence from tau less than for tau less than 0, we have yt is equals to 0, and for t greater than 0, how to calculate the value of yt? So yt is nothing but it is from 0 to t. It is nothing but from 0 to t. We have integration from 0 to t e raised to the power minus alpha e raised to the power minus alpha t minus tau d tau. Why? Because ht minus tau is equals to e raised to the power sorry, it is a, it is not alpha, it is a. So it is a, because ht minus tau is e raised to the power minus a t minus tau u t minus tau. So let us explain how this is coming, how this integral is coming. So we have yt, that is from minus infinity to plus infinity, x tau ht minus tau d tau. This is our equation. Now we can write all these things here. What is x tau? It is simply u tau. What is ht minus tau? It is e raised to the power minus a t minus tau u t minus tau d tau. Now for t greater than 0, yt is equals to 0 to infinity, because we are considering for t greater than 0. What is that value? Because for t greater than 0, only the overlapping region, if we consider the overlapping region, this is our x tau and this is ht minus tau. So basically we are considering this region only, So from 0 tau equals to 0 to t, what is that equation? So equation is basically we have e raised to the power minus a t minus tau into ut minus tau. And what is ut minus tau? It is 1 only. So finally we can write it as 0 to t. It is not infinity. So we can write only from 0 to t e raised to the power minus alpha t minus tau d tau. Now we can put e raised to the power minus alpha t outside, because here we have variation from tau equals to 0 to tau equals to t, because basically the independent variable in this integral is tau. So we can so basically e raised to the power minus sorry, again I am writing alpha. Okay, so this we can put outside. So we have e raised to the power minus at from 0 tau equals to 0 to tau equals to t. So from this tau equals to 0 to tau equals to t, I had put this e raised to the power minus at outside. Then the remaining term we can put inside the integral, that is e raised to the power a tau d tau. Now if we solve this integral, what we will get? E raised to the power minus at, we will get 1 divided by a e raised to the power at minus 1. Okay, so finally what we will get? We will get yt is equals to, okay, we can put this term inside this. What we will get? So finally what we will get? We will get 1 divided by a 1 minus e raised to the power minus at and alpha is greater than 0 and and t is greater than 0, because we have considered that t greater than 0. So let us summarize this in mathematical form. So we have yt. So yt is equals to 0 for t less than 0, and yt is equals to 1 divided by a 1 minus e raised to the power minus at for t greater than 0. So if we consider that if we just consider the unit step function, then we can combine these two equations into single equation. So yt can be written as 1 divided by a 1 minus e raised to the power minus at into ut. So why I have written this in this form? Because ut is equals to 0 for t greater than t less than 0, and it is 1 for t greater than 0. So if we consider that ut is equals to 0 for t, because t less than 0, if we consider t less than 0, then ut is equals to 0. So yt is equals to 0. If we consider for t greater than 0, then we have ut is equals to 1. So we have yt is equals to 1 divided by 1 minus e raised to the power minus at for t greater than 0. So we have considered both cases. Now comes to part B. Now comes to part B of the problem. So what is part B? Part B is yt is equals to ht convolution with xt, and it is equals to minus infinity to plus infinity h tau xt minus tau d tau. So let us draw all the necessary diagrams related to this problem. So we have this. So the first diagram is we have h tau. So h tau is simply, we have this. The graph of h tau is decreasing, e raised to the power minus 8 into ut. So it is decreasing graph. This is our h tau, decaying exponential. So at tau equals to 0, we have 1. Otherwise it is decaying. And what is x minus tau? What is x tau? So x tau is this one is x tau. Now what is x minus tau? Because we need to find out xt minus tau. So what is x tau? X tau is this one. This graph is x tau. Basically this is a time reversal of this. So it is a time reverse. Then for t less than 0 and for t greater than 0 we have two different graphs. So for t less than 0 there is shift on which side it will shift for it will shift in this left hand side. So it is x t minus tau, it is x t minus tau when shift is negative, and when shift is positive we have this graph, this type of graph when shift is positive. So we consider both the cases when shift is positive and when shift is negative. So for t when shift is negative, when t is less than 0 we have the graph will shift in left hand side. It will go away from the origin in left hand side towards the left hand side. And when the shift is positive, when you have t greater than 0, we will see that we will get a positive shift. The graph will move towards the left hand side away from the origin. So this is our figure 2. Let us all the figure comes under that figure number 2. So what is our what is our figure that is required? What are the figures that required for this? So we require this figure and we require these two figures. So let us draw the figure again. So we have h tau. This is our h tau, and the first is considering t less than 0. This is xt minus tau for t less than 0, and this is xt minus tau for t greater than 0. So let us solve this problem first. So from figure 2, if we see the figure 2, so from figure 2, for t greater than 0, for t greater than 0, function, if we see the figure, function h tau and xt minus tau do not overlap, do not overlap, while for t greater than 0 they overlap, while for t greater than 0 they overlap. And what is the overlap reason? The overlap reason is from tau equals to 0 to tau equals to t. Hence for t less than 0 hence for okay, let us see that graph. Let us see the graph. So this is our h tau and this is our x t minus tau. Now for t greater than 0 they will overlap, and for t less than 0 they will not overlap. Okay, so so in previous page, okay, so for t greater than 0, so for t greater than 0 function okay, sorry, here we should write t less than 0. Okay, it is for here we should write t less than 0. Okay, so in for t less than 0, that x tau functions x tau and t minus tau do not overlap, while for t greater than 0 they overlap. And what is the overlapping region? From tau equals to 0 to tau equals to t. Hence for t less than 0, yt is equals to 0, because there is no overlapping. Now for t greater than 0, yt is nothing but 0 to t e raised to the power minus a tau d tau, and that is equals to 1 divided by a 1 minus e raised to the power minus a t. Okay, so we have we can write the output. So yt is equals to 0, for t less than 0, and it is equals to 1 divided by a 1 minus e raised to the power minus at for t greater than 0. So we can combine these two equations and we can write it as yt is equals to 1 divided by a 1 minus e raised to the power minus at into ut. So we can write in this form. So again I am showing you the graph. So this is our h tau, and this is our xt minus tau for t greater than 0, and this it is from tau equals to 0 to tau equals to t. So if we see that for t greater than 0, they will overlap. These two equations, these two graphs will overlap. And what is the overlap reason? It is from tau equals to 0 to tau equals to t. Now for t less than 0, if we see that the product of h tau and xt minus tau is 0. Why is 0? Because if we see that there is no overlapping region, they do not overlap. That's why we have considered that ut function, that is unit step function. So this is our output. So if we see that this output is same, we have this output for yt is equals to ht convolution with xt. Now if we see the previous output, what is the previous output? So the previous output is also 1 divided by a 1 minus e raised to the power minus at into ut, and here we have considered yt is equals to xt convolution with ht. So it is same if we consider xt convolution with ht or ht convolution with xt, we will get the same output. So here the output when we have considered yt is equals to xt convolution with ht is equals to, it is equals to 1 divided by a 1 minus e raised to the power minus at into ut. It is the same output we are getting, and the condition is reversed when we have considered that yt is equals to ht convolution with xt. So you can see that the output is same. Okay, thank you all of you.